A 50-ton monument to engineering might, the Caterpillar D9R is an icon in the realm of heavy machinery. But in a secluded quarry, one of these yellow behemoths is inert, its massive tracks gradually settling into the ground, immobilized by a malfunction that eludes a simple diagnosis. The local dealership has already rendered its verdict, issuing a $30,000 estimate to replace its electronic control module, or ECM. For a machine of this age, such an expense is tantamount to a death warrant, compelling the owner to compare the cost of repair with the scrap value of his motionless asset. This situation exposes a profound weakness in contemporary maintenance practices, an over-reliance on black box diagnostics instead of a deep forensic investigation. The dealer condemned the machine's brain because their computer couldn't communicate with it, yet the symptoms pointed to a more nuanced, systemic problem. We are about to show how the entire 405 horsepower output of a diesel engine can be held captive by a single, unnoticed strand of wire. To appreciate the weight of this diagnosis, one must first grasp the nature of the platform. The D9R is more than just a bulldozer. It's a legacy system engineered around the Caterpillar 3408 HEUI engine. This 18-liter, 8-cylinder power plant is renowned for its mechanical toughness and its capacity to function in conditions that would annihilate lesser equipment. It employs a hydraulically actuated, electronically controlled unit injection system, which serves as a technological bridge between old-school mechanical fueling and modern common rail systems. This design was conceived for extreme durability, capable of withstanding tens of thousands of hours of grueling work cycles if given the correct care. When a machine of this caliber goes down, it seldom does so without some form of warning, making this particular failure a true anomaly. The operator recounted that the dozer didn't run hot, didn't produce smoke, and didn't experience any kind of catastrophic mechanical failure. It simply died in the middle of a push, and then would not restart. The abrupt nature of the shutdown hinted at an electrical interruption rather than a mechanical breakdown. The service report from the dealership, however, told a different story. Their technician had plugged in a diagnostic tool, was unable to connect with the engine controller, and promptly determined that the ECM had experienced a terminal internal fault. The report showed no evidence of pinout voltage tests, no load testing, and no examination of the physical wiring harness. The entire diagnosis was founded on the absence of a digital handshake. In the high-pressure world of heavy equipment service, this kind of approach is distressingly frequent. The cost of downtime for a production machine can often dwarf the price of the parts themselves, creating a powerful incentive to approve swap-and-pray repairs. If a $30,000 computer has a chance of solving the issue, many companies will authorize the purchase just to shorten the diagnostic period. It's a financial decision that values speed above precision, frequently resulting in the replacement of perfectly good components while the original problem remains hidden and unresolved. This institutional tendency to throw parts at an issue is what leads to the premature retirement of otherwise serviceable machinery. For this particular owner, however, the numbers didn't make sense. The D9R, though still a valuable machine, was an older asset. A $30,000 repair for one component, with no assurance of success, brought the dozer perilously close to becoming a financial write-off. The owner sensed that the dealer's assessment was incomplete. If the ECM had truly failed, why did it happen so suddenly? Why weren't there any intermittent problems leading up to the shutdown? These inquiries led to a call for an independent specialist, a forensic technician who sees a machine not as a list of part numbers, but as an interconnected system governed by physics and electricity. The specialist came to the site with a different mission. The aim wasn't to sell a new computer, but to piece together a chronological account of the failure. Experience teaches that while electronic components can fail, they seldom do so in a vacuum without some external trigger. A 3408 ECM is a ruggedized, potted device built to withstand severe vibration and heat. It doesn't just spontaneously expire without a reason. The dealer's report was a conclusion based on a lack of information, whereas the specialist was determined to find tangible proof of the fault. We have to leave behind the abstract world of invoices and service reports and enter the physical environment of the quarry. The machine sits coated in the dust of its final workday, a memorial to deferred maintenance and diagnostic shortcuts. It is here, among the dirt and grime, that the real story of the failure is written, waiting for someone with the patience to decipher the language of voltage, resistance, and continuity. Upon reaching the quarry, the surrounding environment immediately becomes a prime suspect in our investigation. The D9R does not function in a sterile lab. It lives and works in an atmosphere of abrasive dust, intense vibration, and constant thermal changes that all conspire to break down electrical connections. The quarry ground is a carpet of limestone powder, a material that seems harmless when dry, but transforms into a conductive and corrosive slurry when mixed with moisture or hydraulic oil. This dozer has spent the better part of a decade vibrating to the rhythm of its 3408 diesel engine while caked in this substance. Before we even open a toolbox or take out a multimeter, we must recognize that the very air is an antagonist to the machine's electrical system. The quiet of the quarry only accentuates the dozer's stillness, underscoring that this is not a machine at rest, but one that has been conquered by its surroundings. Our process starts with a walk-around inspection, a visual cross-examination of the asset. We are not yet trying to find the specific fault that killed the engine. Instead, we are evaluating the maintenance culture that defined this machine's final operational hours. The state of the undercarriage and the fluid levels provide insight into its mechanical treatment, but the condition of the external wiring reveals how it was handled from a diagnostic standpoint. It is instantly clear that this machine was subjected to a frantic and disorganized attempt at resurrection. The layers of grease and stone dust covering the chassis are mostly untouched, except for a few distinct areas where recent human intervention has left clean patches that stand out like signals of desperation. This leads us to the clear signs of the parts cannon approach. Tucked away in the battery compartment are 4 new Group 31 batteries, their posts shining and free of any corrosion. The starter motor, a substantial Delco unit, also sports the clean, semi-gloss black finish of a recent replacement. In the operator's cab, the ignition switch feels new and resistant, lacking the worn-in feel of the other controls. These parts represent thousands of dollars in spending, installed by previous technicians who were hoping that throwing fresh components at the problem would jolt the machine back to life. It is a tangible record of the swap and pray method. The engine wouldn't crank, so they changed the starter. The lights seemed weak, so they put in new batteries. When these costly guesses failed to produce ignition, they targeted the most expensive component on the schematic, the ECM. A more detailed look at the visible wiring harnesses, however, tells a different story. The protective sheathing, once a supple nylon conduit meant to guard the wires against chafing, has hardened into a fragile shell after years of exposure to heat. It fractures with the slightest touch, leaving the color-coded insulation underneath exposed to the harsh environment. We can see connectors near the transmission that are soaked in oil, a result of capillary action where fluids are drawn up through the wire strands, fouling the contact points. This isn't just a cosmetic issue. It's a breakdown of the dielectric insulation that is supposed to keep electrical current contained. Moreover, we can see the telltale signs of improper field repairs. Cable ties cinched down with extreme force, crushing the wiring loom against steel hydraulic pipes. An over-tightened zip tie creates a stress point where vibration is no longer dampened by the harness's flexibility, but is instead concentrated on the delicate copper strands within. Over thousands of operating hours, this pressure becomes a slow-acting guillotine. These visual observations form our forensic foundation. The machine is mechanically healthy. The engine can be turned by hand, and the fluids are full, but it is electronically unresponsive, a giant paralyzed by the decay of its own nervous system. The dealership saw a computer that was silent. We see a network of wires that have been cooked, shaken, and squeezed until they could no longer transmit a signal. We are now prepared to move past the theories and open the access panels to test the claim of a dead ECM. We climb into the operator's cab to find the diagnostic port located under the dashboard. We plug in our communication adapter, the device that bridges the gap between the machine systems and our diagnostic software. Upon launching the program, we are met with the very same digital silence that had this machine condemned to the scrapyard. The software tries to establish a connection with the engine control module. The progress bar fills, stalls, and then times out. The screen presents the dreaded "No ECM communication" message. This is the precise point where the dealership's technician halted their analysis. For them, this error message was a final verdict. For a forensic specialist, it is merely the opening line in a much longer and more detailed inquiry. To grasp why this error can be so deceptive, one must consider the architecture of the J1939 data link. This is the digital network through which the machine's various components communicate. It functions using a twisted pair of wires that carry a differential voltage signal. When the diagnostic software says "no communication," it is not declaring that the ECM is broken. It is simply reporting that the ECM is not responding. There are numerous reasons for this silence that have nothing to do with the computer's internal health. The data link wires could be broken, or more importantly, the ECM itself may not be receiving the power it needs to activate. This silence is a sign of disconnection, not necessarily a sign of component failure. We shift our focus from the laptop to the physical dashboard instruments. When the ignition key is turned to the on position, a functioning D9R initiates a self-check. The needles on the gauges should sweep, and the various LED warning lights should flash. On this machine, the panel is completely lifeless. The gauges are stuck at their resting points. The warning indicators stay dark. The only indication of power is the dim backlight, which runs on a separate circuit. This complete lack of instrument activity confirms that the ECM is not just ignoring the laptop. It isn't even running its startup sequence. It has lost its primary logic power. This brings us to a psychological pitfall in modern equipment repair. The dependency on diagnostic software has caused the fundamental troubleshooting abilities of many technicians to weaken. When the computer connects and gives them a specific fault code, the technician's role becomes that of a part replacer. But when the computer can't connect, the technician is effectively flying blind. The immediate assumption is that the black box must be the problem, because it's the one component they can't see inside. They conclude that if the laptop can't see the ECM, then the ECM must be dead. This cognitive shortcut leads to the condemnation of perfectly good hardware. They mistake a lack of communication for a lack of function. They see a dead computer. We see a unit that is simply waiting for the command to power on. We must put forward a different hypothesis. The 3408 ECM is a hardened industrial computer, not a delicate piece of consumer tech. It is far more plausible that the ECM is being prevented from activating by an external factor. There are two main possibilities. First, its power source has been cut off. Second, the ECM is being actively held in a shutdown state. These units are engineered with advanced self-protection features. If the ECM senses a critical electrical problem in its sensor network, it will intentionally refuse to boot to avoid an internal failure. It isn't dead. It's in a self-induced coma for preservation. The dealership's $30,000 diagnosis is based entirely on the belief that this silence is irreversible. We are moving forward with the idea that the silence is a protective measure. The laptop has provided all the information it can. It is unable to hear the machine. Consequently, our digital tools are now useless. We cannot solve an electrical issue with software. We must solve it with physics. We close the laptop, unplug the adapter, and pick up the one tool that provides absolute truth in a world of variables, the digital multimeter. It's time to stop asking the computer what is wrong and start measuring the vital signs of the electrical system directly. We find the primary 70-pin connector on the side of the engine, the main conduit that connects the ECM to the machine's electrical system. To check the dealer's diagnosis, we need to run a series of tests that are more thorough than just looking for voltage. We start by back-probing the constant battery power supply found on pins 1, 2, and 3. These are the main lines that deliver operating current to the computer directly from the batteries, completely independent of the ignition switch. With the multimeter set to DC volts, we connect the black probe to the chassis and the red probe to the power pins. The meter reads 25.2 volts. At first glance, this seems to be a good result. The dealer likely saw this voltage, marked it as okay on their checklist, and went no further. However, in forensic diagnostics, a voltage reading on a circuit with no load can be very misleading. This leads us to the crucial difference between voltage and the ability to carry current. A digital multimeter has a very high internal resistance, which means it pulls almost no amperage from the circuit it's testing. Because of this, a wire that has corroded until only a single strand of copper remains will still show full battery voltage on the meter. That one strand is enough to transmit the electrical pressure, but it cannot handle the amperage needed to power the computer. The moment the ECM tries to boot up and draw current, the resistance in that single strand would cause a severe voltage drop, and the supply would instantly fall to zero. To a technician with a multimeter, the power seems fine. To the ECM, there is no power at all. To rule out this possibility, we have to conduct a load test. We unplug the harness and connect a sealed beam headlight, an old-fashioned halogen lamp that pulls about 4 to 5 amps, into the circuit. We use the ECM's power pins to illuminate the bulb. If the wiring is compromised, the light will be dim or won't turn on at all. We connect our test setup. The halogen bulb ignites with a brilliant white light. This confirms that the copper pathway from the batteries to the connector is physically sound and can handle a significant electrical load. The constant power supply is good. The ground circuit, tested on pins 4, 5, and 6 with the same technique, is also solid. The system's foundation is strong. Next, we check the ignition switched power, which is usually on pin 70. This is the wake-up signal. When the operator turns the key, a 24-volt signal travels down this wire, telling the ECM to switch from its low-power sleep mode to its active state. We have an assistant turn the key while we monitor the pin. The multimeter immediately jumps from 0 to system voltage. We also load test this circuit, and it too supports the current. We have now definitively proven that the ECM is receiving a strong power supply, has a solid ground connection, and is getting a clear command to turn on. This uncovers the main puzzle that stumps so many technicians. We have a computer that is receiving everything it needs to function. It has power, it has ground, and it has the ignition signal. Despite this, it won't communicate, and the instrument panel remains dark. According to a standard diagnostic procedure, this is the end of the road. The logic is simple. If the inputs are correct and there is no output, the component itself must have failed internally. This is the exact point where the dealership wrote off the ECM. They checked the inputs, saw they were correct, and interpreted the silence as a sign of death. They concluded that the processor inside the sealed aluminum box had failed. This conclusion, however, fails to consider the intricate internal design of the Caterpillar ADEM system. An ECM that has power but appears dead is rarely truly dead. It is much more likely that the unit is in a state of self-preservation. We need to understand that the ECM doesn't just use power, it also provides it. It takes the 24 volts from the battery and converts it into a regulated power source for its sensor network. If there is a problem with that outgoing power, the computer will deliberately shut itself down to avoid self-destruction. The dealership saw a dead body. We see a patient in a coma, induced by its own safety mechanisms. The multimeter has confirmed the external power is good, which means we must now look at what the ECM is trying to power on the outside. We are now ready to investigate the 5-volt reference circuit. To comprehend why a machine with perfect power inputs can act as if it's dead, we must imagine the internal layout of the Caterpillar ADEM control unit. While we often call the ECM a computer, it's more precise to see it as both a power station and a distribution center. The 24 volts we confirmed at the main connector is the raw energy, but the delicate microprocessors and sensitive sensors throughout the engine cannot use this high voltage, unstable electricity directly from the charging system. Inside the aluminum casing is a specialized voltage regulator, a critical internal part designed to convert that raw 24 volts into a perfectly stable, clean 5-volt supply. This 5-volt line is the lifeblood of the logic system. Without it, the brain is inert and no data can be transmitted. This regulated voltage is called the 5-volt reference, or VREF. It doesn't just stay inside the ECM. The control module sends this power out through the wiring harness to supply the external sensors that monitor the engine's vital functions. The oil pressure sensor, boost pressure sensor, coolant temperature sensor, and throttle position sensor all depend on the specific power line to work. They are active devices. They don't create their own signals, but instead alter the 5 volts they receive from the ECM and send a modified signal voltage back. This design establishes a crucial link. The health of the internal computer is directly connected to the condition of the external wiring harness. This is where the system's weakness lies, and it's likely the cause of the dealership's misdiagnosis. In this generation of engine controls, the 5-volt reference is often a shared rail. This means a single source inside the ECM provides power to multiple external sensors at the same time, similar to how one circuit breaker in a house might power all the outlets in a room. If you were to put a fork in a toaster, the breaker would trip, and the microwave would also lose power. The microwave isn't broken. Its power was cut to prevent the house from catching fire. The D9R functions on the same principle, but with much higher stakes and more costly outcomes. If any single wire carrying that 5-volt reference chafes against the engine block and makes contact with bare metal, creating a short to ground, the current in that circuit will instantly surge toward an infinite level. The laws of electricity dictate that the current will follow the path of least resistance, flowing directly into the steel frame instead of through the sensor. Inside the ECM, the voltage regulator detects this massive, uncontrolled current draw. If it were to continue supplying power, the internal circuits on the board would overheat and melt, permanently destroying the computer. To avert this disaster, the ECM performs a hard shutdown, instantly deactivating the 5-volt regulator. When the regulator shuts down to protect itself, the effect is immediate and widespread. Since the main logic processor is on the same power rail, it also loses its supply. The computer goes dark. Communication with the diagnostic laptop is lost. The instrument cluster goes dead. The machine seems to have failed completely. But this isn't a failure. It's a self-preservation mode. The ECM is essentially holding its breath, waiting for the danger to pass. The dealership's technicians saw a computer that wouldn't power on and assumed it was faulty. We now realize that the computer is refusing to power on because it is protecting itself from an external threat. This completely changes our diagnostic strategy. We are no longer searching for a problem inside the control module. We are searching for a problem out in the field. The ECM is working exactly as it was designed to. It is successfully preventing an electrical fire. The silence we're observing is the sound of a safety system doing its job perfectly. The issue isn't the black box. The issue is a rogue electrical path somewhere in the hundreds of feet of copper wire surrounding the engine. The dealer blamed the police officer for not answering his radio, not realizing the officer was busy restraining a suspect. To confirm this theory, we don't need to cut open the harness or replace the computer. We just need to remove the electrical load. If the ECM is shutting down because a sensor circuit is shorted, then unplugging the sensors should eliminate the short and allow the ECM to power up. It's a method of elimination, a systematic removal of variables. We will disconnect the sensors one by one, effectively isolating the ECM from the potential problem. If we unplug the engine harness and the computer suddenly connects with our laptop, we will have proven that the $30,000 quote was for a perfectly functional part, and the real problem is a 50-cent piece of copper wire hidden somewhere in the dark. We must now move from the theory of the short circuit to the physical search for the damaged component. The shift from theoretical diagnosis to physical confirmation means leaving the relative cleanliness of the cab and descending into the engine's architecture. The theory of a shorted 5-volt reference is a good one, but proving it requires a careful dissection of the engine's electrical system. We are no longer working with data streams or error codes. We are working with copper wire, insulation, and the harsh reality of a 30-year-old wiring harness that has been heat cycled into a semi-rigid form. To locate the fault, we must follow the physical path of the electrons through the V of the engine, a dark, oil-covered valley between the cylinder heads where the most important connections are located. We start by unplugging the main 70-pin connector again. This isolates the engine control module from the entire machine's wiring. If our theory is correct, that the ECM is protecting itself from a short, we should be able to measure that short directly at the harness connector. We set our multimeter to measure resistance, specifically looking for continuity to ground. We find the pin for the sensor supply voltage, which is typically an orange wire on Caterpillar schematics of this era. We insert the red probe into the harness socket for the sensor supply and touch the black probe to the cast iron engine block. In a healthy circuit, the meter should display OL for overlimit, signifying infinite resistance. The wire carrying the voltage should be completely insulated from the machine's frame. Instead, the meter lets out a continuous, high-pitched beep. The display reads 0.3 ohms. This is undeniable proof. It confirms with physical certainty that the 5-volt supply line has a direct connection to the chassis ground somewhere in the maze of the engine compartment. The ECM was never the issue. The ECM was the casualty. The short is real, and now we have to find it. Our search method is a process of elimination called splitting the system. The engine harness isn't one continuous loop. It's like a tree with branches that extend to different sensors. By unplugging the sensors one by one, we are essentially trimming branches from the tree. If we disconnect a sensor and the short on our meter vanishes, we'll know the problem is in that specific sensor or its connecting wire. If the short persists, the problem is further up the main harness. We begin with the most easily accessible parts. We reach down to the front timing cover to disconnect the primary and secondary speed timing sensors. These magnetic pickups inform the computer about the crankshaft's position. We unplug them, but the meter keeps beeping. The short is still there. We move on to the atmospheric pressure sensor and the turbocharger boost pressure sensor, which are located high on the intake manifold. We disconnect their plugs, checking the terminals for any signs of corrosion or oil. The meter remains steady at 0.3 ohms. The fault is not in the sensors. It must be in the wiring that connects them. We now have to follow the harness deeper into the engine, tracing the main loom as it runs toward the back. This is challenging terrain. The 3408 is a densely packed engine, and the wiring is routed very close to the block to stay clear of the extreme heat from the turbocharger pipes. We slide our hands along the loom, feeling for any flat spots, kinks, or areas where the protective sheathing has been worn away. We are searching for a rub point, a common failure mode where vibration has caused the harness to wear through its own protection until the copper wire makes contact with steel. We arrive at a junction block where the harness divides to supply the oil pressure sensor and the coolant temperature sensor. We separate this rear portion of the harness from the main trunk. Instantly, the beeping from our multimeter ceases. The screen flashes to OL. The short is gone from the main connector. This is our breakthrough. By isolating the rear branch, we have eliminated 80% of the wiring from our search. We now know the fault isn't in the computer, the front sensors, or the main harness. The problem is hiding in the specific section of wiring that runs behind the cylinder head, a dark and hard-to-reach area between the engine block and the hydraulic pumps. We have narrowed our search from the entire machine down to a 2-foot section of dirty, oil-soaked wiring. We reconnect the main harness and direct our flashlight into the space behind the hydraulic pumps. This area is known to be problematic on the D9R chassis. It's a blind spot for mechanics, a place where dirt and debris accumulate, and where the harness is exposed to the intense, harmonic vibrations of the hydraulic system. We can't see the wire just yet, but the diagnostic process tells us it's there and it's damaged. We prepare to dismantle the clamping system to bring the hidden copper into the light. The layout of a D9R engine compartment is not made for human access. It is engineered for power density. The area we have pinpointed, the space behind the hydraulic pump assembly, is a busy intersection of high-pressure steel lines, cast iron components, and the engine block itself. It's a dark, greasy cavity where heat builds up and dissipates slowly. To get to the harness, we have to squeeze ourselves into the frame rails, working around the heavy steel guards that shield the machine from the quarry environment. Our flashlight beam pierces the darkness, revealing a section of wiring that, at first, seems to be fine. The corrugated nylon sheathing is covered in a thick layer of oil and limestone dust, a protective coating that conceals the true condition of the wires inside. However, forensic analysis teaches that the external appearance of the loom can be deceptive. The real story of the failure is often found on the inner surface of that nylon tube. We locate the specific mounting points, known as P-clips, rubber-lined steel clamps that fasten the harness to the engine block to prevent it from moving. On a machine that vibrates with the intensity of an 18-liter diesel engine, these clamps are the only thing protecting the wiring from abrasion. We notice that the clip holding this particular branch of the harness is bent out of shape. It is not suspending the wire bundle as it should. Instead, it is pulling it tightly against a hydraulic pipe. This steel pipe carries high-pressure fluid to the implement control valve, and during operation, it vibrates with the machine's hydraulic rhythm. We have discovered a point of contact where two rigid components, the steel hydraulic line and the hardened wiring harness, have been forced into a destructive relationship. Using a pair of diagonal cutters, we carefully snip the zip ties and unbolt the P-clip to relieve the pressure. The harness is stiff, its insulation having been cooked into a brittle plastic by years of heat exposure. As we pull the loom away from the hydraulic line, a small amount of black plastic dust crumbles onto the frame. We carefully slice the nylon conduit open lengthwise, peeling it back to reveal the individual wires. The color coding has faded, but the damage is immediately apparent. We separate the strands, moving aside the twisted data link pairs and the heavy power wires until we find our target. It is a single wire with orange insulation, the standard Caterpillar color for the 5-volt sensor supply. There, on the underside of that orange wire, is the tiny detail that 3 engineers and a diagnostic computer all missed. It's a wound no bigger than a grain of rice. The engine's vibration, over thousands of hours, has caused the hydraulic line to act like a slow-moving file. It has ground its way through the nylon loom, through the electrical tape, and finally through the orange insulation of the wire. The copper conductor is visible, shining faintly in the bright beam of our flashlight. Around the exposed copper is a small halo of black soot, carbon tracking left by the electrical current arcing from the wire to the steel pipe. This minuscule patch of exposed metal, less than 2 millimeters across, is the epicenter of the entire failure. When the engine vibrated, the copper touched the steel hydraulic line, which is connected to the chassis ground. In that split second of contact, the 5-volt rail was shorted to ground. The ECM detected this direct short and immediately activated its self-protection mode, shutting down the entire system to save the voltage regulator. The machine didn't fail due to a complex computer malfunction. It failed because of simple friction. The dealership was about to replace a computer because a wire had rubbed against a pipe. The true cause of this failure, however, is not the wire itself, but the absence of a 5-cent part. Looking closely at the P-clip's mounting point, we see signs of a previous repair. The bolt hole on the bracket is larger than the bolt, designed to accommodate a rubber grommet or a standoff that would ensure the harness floats away from the steel lines. That grommet is gone. At some point in the machine's past, maybe 5 years ago, maybe 10, a mechanic removed this harness to work on a pump or replace a hose. When they put it back together, they either forgot the grommet or decided it wasn't important. They bolted the clamp directly to the metal, changing the routing geometry by a tiny fraction of an inch. That tiny fraction of an inch was enough to let the harness make contact with the hydraulic line. This finding highlights the economic absurdity of the situation. We are looking at a failure that cost the owner tens of thousands of dollars in lost productivity and nearly sent a 50-ton machine to the scrap heap. The dealer's $30,000 quote was essentially a penalty for a missing rubber washer. The ECM was never faulty. It was simply reacting to a physical attack on its wiring. We have confirmed the value of the forensic method. By looking past the black box and focusing on the physics, we have uncovered the truth. The machine doesn't need a new brain. It needs a piece of heat shrink tubing and a careful hand. The puzzle is solved, but our work is not done. We must now surgically repair the damage and make sure this specific failure can never disable the machine again. We commence the repair not with a simple pair of pliers and some electrical tape, but by preparing a clean surgical area. The reliability of the 5-volt reference circuit is critical. Even a small amount of resistance from a poorly made splice can cause sensor readings to drift, leading the ECM to calculate incorrect fuel delivery or generate false error codes. We carefully separate the damaged orange wire from the bundle, creating enough slack to work on the damaged section. Using precision wire strippers, we remove the insulation for 1 inch on either side of the abrasion. The copper strands, having been exposed to air and oil, show signs of oxidation, a dull tarnish that can impede current flow. We mechanically clean the strands until they are bright and shiny before making any connection. To repair the break in the copper, we don't just twist the wires together. We use a high-quality uninsulated butt connector, crimped with a ratcheting tool that creates a cold weld between the wire and the terminal. For a circuit this sensitive, however, a mechanical crimp is just the beginning. We follow up by applying rosin core solder, heating the connector until the solder flows deep into the wire strands. This forms a solid metal bond that is immune to the high-frequency vibrations of the diesel engine. Once the splice cools, we slide a piece of dual wall, adhesive-lined heat, shrink tubing over the repair. This is essential. Standard tubing is not sufficient for this harsh environment. When we apply heat, the inner wall of this tubing melts into an adhesive that seals the wire, creating a waterproof barrier that will prevent oil, water, or dust from ever reaching the conductor again. Fixing the wire, however, only addresses the symptom. If we were to simply put the harness back where it was, the vibration would eventually ruin our repair. We must correct the root cause, the lack of proper strain relief. We find a new rubber-cushioned P-clip, and, most importantly, the missing standoff spacer from our parts kit. We reroute the harness, creating a service loop, a deliberate, gentle bend in the wire that allows it to flex with the engine's movement without being pulled tight. We bolt the clamp in place, making sure there's a clear air gap between the nylon loom and the steel hydraulic line. The harness now floats, suspended by the rubber cushion, protected from the friction that almost destroyed the machine. We secure the loom with cable ties, but we don't use pliers to tighten them. We use hand tension to ensure the plastic conduit is supported, not crushed. With the physical problem corrected, we begin the reassembly process. We move back up the engine, reconnecting the sensors we unplugged during our diagnosis. The turbo boost sensor, oil pressure sensor, and timing sensors are all clicked back into place. We check the seals on each connector, applying a light coat of dielectric grease to the rubber gaskets to keep them flexible and watertight. Finally, we return to the main 70-pin connector. We align the jack screw and tighten it by hand until it is fully seated, feeling the pins make contact. The machine's nervous system is now fully restored. We climb down from the tracks to the battery box to reconnect the main power. The 4 Group 31 batteries are reconnected, and the heavy positive and negative cables are torqued to the correct specification to prevent any arcing. As the final ground cable makes contact with the terminal, we listen carefully. There is no spark, which indicates that the short circuit is gone and there is no unwanted current draw. The system is now live. We do one last visual check of the engine compartment, making sure no tools have been left behind and all covers are secure. The machine is physically ready. The theory has been proven, the damage has been repaired, and the protection has been restored. All that's left is to climb into the cab and turn the key to see if the digital brain will come back to life. We get comfortable in the worn operator's seat, surrounded by the quiet of the quarry. The physical repair is done, but in forensic engineering, the job isn't over until the system proves it can function under its own power. We are not just looking for it to start. We are looking for a complete return to factory performance. We put the key in the ignition, a simple mechanical action that starts the digital sequence we have worked for hours to restore. We turn the key to the on position, and for the first time since the machine was written off, the cab comes to life. The instrument panel, which was previously dark and unresponsive, now sweeps its gauges from low to high and back again, a self-check procedure that confirms its internal systems are working. The warning light panel illuminates with a bank of LEDs, cycling through its checks. Most importantly, the wait to start light glows amber. This is more than just a light. It's a confirmation that the ECM is now active, monitoring the air temperature and activating the grid heaters. The machine's brain has awakened from its coma. We immediately look at the diagnostic laptop on the passenger seat. The software, which had previously failed to connect, now shows a green status bar. The screen fills with live data. We can see the coolant temperature, intake manifold pressure, and battery voltage. The no communication error is gone, replaced by a logged fault for the 5-volt sensor supply, a digital record of the event that silenced the machine. We clear the fault log. The system is now clean. We get ready to start the engine. The Caterpillar 3408 is a HEUI engine, hydraulically actuated, electronically controlled unit injection. It doesn't start instantly like an older mechanical diesel. When we turn the key to start, the engine has to spin fast enough to drive the high-pressure oil pump, which builds enough hydraulic pressure in the rail to physically operate the fuel injectors. We turn the key to the start position. The heavy Delco starter engages with a solid thud, and the massive crankshaft begins to turn. We watch the laptop screen closely, ignoring the sound of the engine for a moment to focus on the data. We are monitoring the injection actuation pressure reading. It climbs quickly: 100 psi, 300 psi, 800 psi. At 870 psi, the ECM gives the command for the injectors to fire. The engine ignites. It's not a hesitant sputter. It's a powerful, decisive start. The 8 cylinders fire in order, and the machine shakes off the stillness of its long shutdown. The idle quickly settles at a steady 700 RPM. The sound is distinctive. The deep, rhythmic rumble of a large displacement diesel engine breathing through a turbocharger. We check the oil pressure gauge on the dashboard. It immediately rises into the green zone. The alternator starts charging, sending 28 volts back to the batteries. The machine is running, but we still need to verify that our repair can withstand the very environment that caused the failure. We leave the engine idling and get out of the cab, taking the laptop with us. We go back to the engine compartment, where the heat and vibration are already intensifying. This is the shake test. We watch the 5-volt reference value on the screen. It holds perfectly steady at 5.00 volts. We reach into the engine bay and physically move the harness near our repair. We push, pull, and twist the loom, simulating the intense harmonic vibrations of a heavy workload. The voltage on the screen never changes. The repair is mechanically secure. The copper wire is now floating safely in its new sheathing, protected from the steel that once grounded it. The sensor supply is stable. The nervous system is sound. We climb back into the cab and increase the engine speed to high idle. The whistle of the turbocharger creates a high-pitched sound over the roar of the exhaust. We lower the blade, engaging the hydraulics. The system handles the load without any issue. The engine governor responds, adding more fuel to maintain RPM against the hydraulic load. There are no active fault codes. There are no warning lights. The D9R, which was just hours from being cut into scrap, is now ready to move Earth. The transformation is complete. We have gone from a silent, motionless liability to a fully functional, revenue-producing asset, all because we refused to accept the diagnosis of a machine that couldn't speak for itself. The final bill for this repair did not include a $30,000 computer. It listed 3 hours of labor, 1 butt connector, a bit of solder, and a single rubber grommet. The total cost was a tiny fraction of the dealership's estimate, a financial win that highlights a crucial lesson in modern maintenance. Diagnostic software is a valuable tool, but it is not a substitute for a solid understanding of electrical principles. The D9R was never really broken. It was just waiting for someone to listen to what it was truly trying to say. If you appreciate in-depth technical analysis and the preservation of classic machinery, make sure you subscribe.